Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to the Computer Architecture and Assembly Language class. Today we are beginning our journey into fascinating world of computer architecture and assembly language. Before we start, as you know that this course requires digital system fundamentals and introduction to computer organization and as prerequisites. Since you have already completed these courses, so I will be building upon concepts you have already learned in those courses, right? So let's take a look at what we aim to achieve by the end of this lecture. Okay, first we will define what computer architecture actually means and why it's so important for understanding how computer systems are organized. Next, we will identify the key concepts and the components of a computer system. This includes the CPU, which is the brain of the computer, memory, where data is stored, and input-output devices, which allow us to interact with the machine. Okay, then we will look at instruction set architectures or ISAs. Specifically, we will compare two major type which are CISCs, which stands for Complex Instructions Set Computer, and RISC, which stands for Reduced Instruction Set Computer. Finally, we will learn how to determine computer performance. We will calculate execution time based on instruction count, clock rate, and cycle per instructions, which is CPI. So these outcomes will give us a solid foundation for understanding how hardware and software work together. Okay, this slide show the complete picture of how a computer system works. So I hope that you are already familiar with all those components and processor. So let's briefly start with the flow of data. First, data enters the computer from the outside world through input devices like the keyboard or mouse. Then this data is kept in the memory until it is required. When the computer is ready to process this data, the data path requests it from memory and performs the necessary operations. So all of this is controlled by the control unit, which directs the entire process. So once processing is complete, the data is sent back to the outside world through the output devices like the printer or any display monitor, projector, anything like that. Now let's look at the five main components of every computer, which are shown in this diagram. So first is the processor or CPU, which consists of two parts: the control unit, which act as the brain and directs operations, and the data path, which does the actual processing and serve as the brawn. Okay, so next is memory. Memory is where program and data live while they are running. So memory is passive, meaning it only stores information and does not process it. Input devices brings data into the computer. Okay, and these includes the keyboard and mouse, or maybe your microphone and all such type of devices. Output devices uh, which send data out of the system. These include the display and the printer, or might be the speakers, okay, and such type of other relevant devices. Storage devices like disks hold program and data when they are not running. So this is where information lives long term, okay, like the hard disk in your computer, which is in the form of HD or SSDs. So all these components are connected by a bus, which is communicating pathway that allows them to transfer data back and forth. This basic structure applies to every computer from the earliest machines to the most modern ones. Okay, so this is the main architecture of all the computer systems. Okay, this slide gives us some context on how computers have evolved and what we will be studying. So, first, computer technology has changed rapidly over the decades. Uh, we have progressed from vacuum tubes to transistors, then to integrated circuits, and then to very large scale integration, and now on system on chips integrations, where an entire computer fits on a single chip. A key observation in this field is Moore's law, which state that number of transistors on a chip doubles approximately every 1.5 years. This has led to exponential growth in both memory capacity and processor speed, driven by advances in technology and hardware designs. Okay, so if you see from the earliest history, so the memory and the processing power, it increased exponentially. Okay, so based on this law. So here is a funny example to put this progress in perspective. So if consider that if the aviation industry have advanced at the same pace as the computer industry, so we could fly from KLIA to New York in just 10 minutes and only for 10 ringgit. Okay, but unfortunately the aviation field haven't advanced at the same pace as the computer industry. So there is quite a difference in all both these fields. Okay, now let's look at what we will be learning in this course. So we will understand this that how computers actually work and learn to distinguish between good and bad design choices. So we will study assembly language programming, which allow us to communicate directly with the hardware. Finally, we will examine issues that what affect modern processors, such as the cache and pipelines, which are critical for achieving high performance. Okay, this slide explains why we need to study computer architecture at the right level of abstraction. The CPU consists of two main parts, the data path, which performs data processing operations, and the control, which directs the data path on what to do. These components are implemented using millions or even billions of transistors on a single chip. Each transistor is a tiny electronic switch. So it is impossible to understand how a modern processor works by looking at individual transistors. Therefore, these are simply too many and they are too small to analyze one by one. So we need a high level of abstraction. Instead of focusing on individual transistors, we study the organization and architecture of the CPU. So this allows us to understand how instructions are executed, how data flows through the processor, and how the control unit manages everything without getting lost in the electric details. Okay, so here we introduce the concept of abstraction, which is essential for managing complexity in computing. Delving into the depth of a computer system reveals more detailed information, but there is a trade-off. An abstraction omits unwanted details and help us cope with complexity. It allows us to focus on what is important and at a given level without being overwhelmed by lower level details. Let's look at the figure on the right to see how abstraction helps a programmer. At the highest level, we have a high level language program written in the C language. This code is readable and use familiar construct like variables and use this code is readable and it use familiar construct like variables and functions. Here we have a simple swap function that exchange two elements in the array. So the C compiler translates this high level code into an assembly language program, in this case for the MIPS architecture. MIPS is microprocessor without interlocked pipeline stage, and we will be using MIPS for the assembly language in this course. Okay, coming back to this, assembly language uses mnemonics like LW, SW, and JR for like LW is used for load word, SW is used for store word, and JR is jump register. So these are still somewhat readable but much closer to the hardware. The assembler then converts this assembly code into the machine language. So this is the actual pattern of ones and zeros that the computer hardware understand and executes. So how does abstraction help the programmer? This programmer can write in C without needing to know the specific assembly instructions or the binary patterns. So the compiler and the assembler handle the translation automatically. This allows the programmer to focus on solving problems and implementing algorithms rather than worrying that how it should be converted to the assembly language or the machine language. So the abstraction layers hide the complexity of the underlying machine instructions, which are for the assembly language or for the this machine level code. So this is how this abstraction helps the programmer. Okay, so this diagram shows the critical role of the instruction set architecture. The instruction set sits at the boundary between software and the hardware. It acts as the bridge or interface that allows software to communicate with the underlying hardware. Software, including operating system and application, is written to understand and use this section set, while hardware, including the processor and memory, is designed to execute these instructions. So the instruction set architecture defines exactly what instructions the computer can execute and how software can interact with the hardware. Let's say a programmer needs to add two numbers. For example, on the software side, above the ISA line. So a C programmer writes C equals to A plus B, for example. The compiler converts this into the assembly interaction, which is add C, comma A, comma B. And then there is the ISA layer, which is the bridge. The add instruction is part of the ISA. So it defines exactly what add means, what format it has, and how registers are used. So on the hardware side, below the ISA line, so the control unit converts this add instruction. It tells the data path to get values from the registers where A and B are stored. So the ALA then performs the actual addition, and then the result is stored back in the register for C. So this IA is like a contract. Software promises to use only instructions defined in the ISA, and hardware promises to implement those instructions correctly. So the software never needs to know how the ALU work inside, and the hardware never needs to know that what the original C code looks like. So the instruction set architecture is very important abstraction in the computing. It serves as the interface between hardware and low level software. It standardizes the instructions, machine language, bit patterns, register names, and memory addressing that software can use. So the main advantage of this abstraction is that it allows different implementation of the same architecture. For example, different processor models from different manufacturers can all run the same software as long as they implement the same instruction set. And the disadvantage is that sometimes it prevents adding new innovations. Once an instruction set is established, changing it back, it can break compatibility within software within the existing softwares. So here are some examples of Modern instruction set architectures 18 to 86, which includes Pentium and K6 processor, PowerPC, DEC Alpha, MIPS, which we will be using, Spark, HP, and Motorola. Each of these defines its own set of instructions and machine learning format. Okay, so this slide can explains the two main types of instruction set architectures. The instruction set architecture, or ISA, defines the set of instructions a CPU can execute and how these instructions are formatted. So different computer architecture have different ISAs, which influence how software interacts with the software. CISC is the first one, and CISC stands for Complex Instruction Set Computer. CISC architecture have many instructions, including complex one that can perform multiple operations in a single instruction. This can make assembly programming easier but requires more complex hardware. Okay, in the RISC stand for Reduce Instruction Set Computer. RISC architecture have fewer simple instructions, so each instruction performs one basic operation, and complex operations are built by combining multiple simple instructions. So this allows for simpler and faster hardware design. So it is important to note that modern CPUs often incorporate elements of both architectures, blurring the lines between them. So, for example, x86 CPUs, which have CISC heritage, it use microcode to translate complex instructions into a simpler micro operations that are executed in a more RISC-like fashion. Ultimately, the choice between CISC and RISC depends on factors such as performance requirements, energy efficiency, and compatibility with existing software. So some processors like ARM are known for their RISC-based designs. Other like Intel and AMD x86 processors incorporate elements of both to balance performance and the compatibility. Okay, so this slide details the key characteristics of CISC, or complex instruction set computer architectures. First is the instruction complexity. CISC architectures features a wide range of complex instructions that can perform multiple tasks in a single instructions. These instructions are typically variable in length, meaning different instructions can occupy a different number of bytes. Second is microcode. So CISC CPUs often use microcode to implement complex instructions. Microcode is a lower level set of instructions built into the processor that breaks down each complex instruction into simpler steps that hardware can execute. Third is the memory access. So CISC architecture tends to have memory-based addressing modes, allowing instructions to operate directly on data in memory. This can result in fewer instructions per program, but makes each instruction more complex. Fourth is the pipeline stage, and in CISC CPUs may have longer instructions. Uh, Actually, it has the longer instructions pipeline due to the complexity of the instructions, and this can lead to slower clock speed but potentially fewer instructions needed to complete a program. Fifth is the code density. Okay, CISC instructions tend to be more memory intensive due to their complexity, potentially leading to the large program size compared to RISC architecture. And the sixth is legacy support. Many older computer architectures, such as x86 architecture used in most personal computers, are CISC based. So they maintain backward compatibility with earlier generations, which can result in complex and sometimes inefficient instruction sets. So understanding these differences help us appreciate the evolution of computer architecture and the trade-offs between performance and complexity. This slide details the key characteristics of RISC. or reduced instruction set computer architecture. Okay, first is instruction simplicity. RISC architectures have a smaller and more simplified set of instructions with a focus on performing basic operations efficiently. So instructions are typically of fixed length, which makes fetching and decoding them simpler and faster. Second is no microcode. RISC CPUs typically avoid microcode and instead rely on hardwired control units for instruction executions. This means that each instruction is directly implemented in hardware, making execution faster. While in the CISC, actually, the microcode use both the hybrid of, the software and the hardware implementation. Third is load store architecture. RISC architectures follow a load store model, meaning that only load and store instructions can access memory directly. All other operations like arithmetic and logic must use registers. So this promotes register-based data manipulation, which is much faster than memory access. Okay, so as you know, in the memory hierarchy, the execution in the register is much faster as compared to the main memory, which is the RAM. Okay, the fourth is shorter pipeline. So RISC CPUs often have shorter instruction pipelines, allowing for faster clock speed and reduced latency. However, this can lead to potentially more instructions per program since complex operations must be broken down into multiple simple instructions. Fifth is the code density. So RISC instructions tend to be more compact, resulting in smaller program size and more efficient memory usage compared to some CISC implementations. Sixth is the efficiency and performance. So RISC architecture prioritize the efficient execution of simple instructions, making them well suited for high performance computing and pipeline techniques. Seventh is the simplified addressing modes. So in RISC architectures typically have fewer addressing modes, which simplifies the instruction set and reduces hardware complexity. Okay, so computer architecture is not just one thing. It consists of the two main components actually. So the first one is ISA, instruction set architecture. This is the abstract interface between hardware and software, which we just saw in the recent slide. So it defines the instructions, registers, memory addressing, and data types that programmers and compilers can use. And the second is machine organization. So this is the physical implementation of the ISA. It includes the data path, control unit, memory system, and how all these components are connected and optimized. So computer architecture equals instruction set architecture plus machine organization. Both are essential to understanding how a computer system works. Okay, so now coming to the computer architecture. This slide shows that where computer architecture fits within the complete computer stack. At the very top, we have the application, which is what user interacts with directly. Okay, like if when now as you are listening and watching to this lecture, you might be using it in the iTalim or the YouTube. Okay, so that is the your application side. So we are interacting with this layer directly. So below that there are the high level language HLL, operating system, okay, compiler and firmwares. So the compiler translates high level code into instructions and the operating system manage the resources. Okay, next we have the instruction set architecture. So right below the software side, there is the instruction set architecture. So this is the critical interface we discussed earlier. Notice how everything above this line, including application, compiler, operating system, and firmware, are the part of the software. So everything below this line is the hardware. So everything above this line is software and everything below this line is the hardware. So the below ISA, we have the instruction set processor and IO systems, followed by the data path and control. These are the hardware components that implement the ISA. So going further down, we have digital designs which deal with the logic gates and flip-flops. So below that is the circuit design which deals with the transistors and the electrical components. Finally, at the bottom, we have layout, which is the physical placement of the components on a silicon chip. So I hope you guys already studied about the digital designs, the logic gates, flip-flops, and all those things, that how they combinedly make a circuit to perform the instructions. So this diagram shows how computer architecture, specifically the ISA layer, serve as the vital bridge between the software and the hardware, abstracting away the lower level implementation details. Okay, now coming to the computer architecture, this slide provides a comprehensive definition of computer architecture. Computer architecture refers to the design and organization of the various components that makes up a computer system. It encompasses both hardware and software aspects and defines how they interact to perform computational tasks. So computer architecture involves making decisions about the organization and functionality of the CPU, memory hierarchy, input and output systems, and other critical components. So there are three key aspects of computer architecture covered here. First, the instruction set architecture, which we already discussed in the details. So this defines the set of instructions that a CPU can execute and the format of these instructions. The ISA serves as the interface between software and hardware, allowing programs to communicate with and control the hardware. Second, the memory hierarchy. So computer architects design memory systems that include various level of storage, such as registers, cache, main memory, and secondary storage like hard drives or SSDs, which are solid state drives. So the memory hierarchy is critical for managing data storage and accessing it efficiently. Hope you have already studied it in details in your ICO and in digital systems. So the third one is the CPU, the central processing unit. It is the heart of the computer, responsible for executing instructions for programs. So computer architects design CPUs to maximize performance, considering factors like instruction execution pipelines, clock speed, and micro architecture. The next one is input output system. So computer architecture includes the design of input and output system, which allows data to be transferred between the computer and external devices such as keyboard, displays, and the storage devices. Fifth part is the interconnection and the bus systems. So architects designed the communication pathways called buses that connects various components within the computer. Of course, to make all these components functional as a one unit, there needs a connection. So these ensures data and control signals can flow efficiently between the CPU, memory, and I/O devices. Sixth one is the parallelism and pipelining. So modern computer architecture often incorporate parallelism and instruction pipelining techniques to enhance performance. Basically, these approaches allow multiple instructions to be executed simultaneously or in overlapping stages, significantly increasing throughput. Seventh is the power efficiency. So energy efficiency is an increasingly important consideration in computer architecture. So architects strive to design systems that delivers high performance while minimizing power consumption, which is especially critical for mobile and embedded devices. Since you know that with the advent of these machine learning algorithms and AI and blockchain, so it it all requires a lot of the computation power, and which that computation power, it needs the power. Power, that's why the architects tend to develop the systems which are the power efficient, so they can perform the high execution efficiently. So the computer architects balance design constraints like performance, power efficiency, cost, and compatibility. They shape systems from PCs to embedded devices. Understanding architecture helps hardware designers build efficient systems and software developers to optimize the performance and efficiency. Okay, so here are the some key concepts of computer architecture. First is the central processing unit or CPU. The CPU is the core processing unit of a computer. It performs arithmetic and logical operations and executes program instructions. I hope you studied all those things in your earlier courses as well. So we will just quickly go through all these architecture components. So the arithmetic logic unit, the actually the CPU has these main components, which is the arithmetic logic unit (ALU), and all the basically, ALU is responsible for performing mathematical and logical operations like addition, subtraction, and comparison. Then there is the control unit, and it manages the execution of instruction. It fetches instruction from memory, decodes them to determine that what needs to be done, and coordinates the other components. Then within the CPU, there are registers, which are high speed, small capacity memory locations. So these are used for temporary data storage and manipulation. So they are fastest type of memory in the system. Hope you have seen in the, we will see in next in the memory hierarchy that how they are fastest and but the smallest in size. So the second is the memory hierarchy. So computer systems have uh, a memory hierarchy that includes various level of storage, each with different capacity, speed, and cost. So at the top, registers are the fastest and smallest located within the CPU. Okay. Next is the cache memory. Cache is faster than main memory but smaller in capacity. It serves as a buffer between CPU and main memory, storing frequently used data for the quick access, like whenever your any program is being executed, that sits in the main memory. So next is the secondary storage. It is the slower than the main memory but offers much greater capacity, like your systems have the hard disks or SSDs. So this includes hard drives, solid state drives, which store data permanently even when the power is off. So the tertiary storage, which is the optional, it's used for the long-term archival storage and backups such as magnetic tape or the optical discs. Okay, the third key concept of computer architecture is the input and output subsystem. The I/O subsystem enables communication between the computer and external devices. So, input devices such as keyboard, mice, and sensor, which allows users to provide data and command to the computer. Output devices like displays, printers, and speakers, it provide feedback and present results to users. Next are the I/O controllers, which manage the flow of data between the CPU, memory, and I/O devices. They handle the complexities of device communication. And buses are communication pathways that connect various components, including the CPU, memory, and I/O devices, allowing them to transfer data. Okay, so the fourth key concept is the system interconnect. This includes the buses and communication pathways that connect the CPU, memory, and I/O devices. It ensures data and control signals flow efficiently between all the components of the computer system. Okay, the next one, fifth, is the instruction set architecture. The ISA defines the set of instructions that the CPU can execute. It includes machine level instructions specifying operations like arithmetic, logic, data movement, and control flow. As we have seen, the ISA serve as the critical interface between software and hardware. Okay, so the sixth is clock and timing. Basically, the computer architecture include a clock and timing system that synchronizes the operations of various components, ensuring proper coordination and sequencing of tasks. The clock generates regular pulses that drive all activities. Seventh is power supply and cooling. These components provide the necessary electrical power to run the computer while maintaining safe operating temperatures, because when there is the processing and CPU execute the instruction, so it emits the heat and it heat up. So a cooling system such as the fans and heat sinks dissipates excess heats generated by the components during operation. As I mentioned earlier, that with the advancement, of all these machine learning and AI systems and blockchain, now even some data centers, some companies, they are developing their data centers under the sea, because with these techniques, they save the cost to cool down the servers and the CPUs. Okay, so eight is the micro architecture. The microarchitecture refers to the specific design and organization of the CPU's internal components, including its instruction pipeline, execution units, and the memory hierarchy. So different microarchitectures can implement the same ISA with varying performance and efficiency. So it means the ISA is the same, but with this different microarchitectures, they can improve the performance and the efficiency. Ninth is the I/O ports and interfaces. So these components facilitate the physical connections between the computer and external device. Like your computer and your laptop have different ports. So they include the USB ports, audio jack, network interfaces, and expansion slots for adding additional hardware. 10th and the last is the firmware and BIOS, or UEFI. So basically, firmware is the software stored on the non-volatile memory that initializes the computer hardware during boot up and provides low-level control and configuration options. So it is the first code that runs when you power on the computer. When you turn on the computer and till your operating system loads. So in between there is the BIOS or UEFI, which executes first. It checks actually all the communication between your hardware and the operating system, and then it loads the operating system to do the further operations. Okay, these key components collectively define the architecture of a computer system, determining its capabilities, performance, and functionalities. Okay, computer architects and engineers carefully design and optimize these components to achieve specific objectives such as the high performance, energy efficiency, and cost effectiveness depending on the intended use of the computer. So from the CPU to the firmware, every component play a vital role in making the computer function as a cohesive system. Okay, now coming back to our assembly language. So here we identify the types of people who work with assembly language. First, the machine designer, who must implement the instructions and make trade-offs regarding instruction functionality. So understanding assembly helps them to design efficient hardware. Second are the compiler writer. And they because the compiler writer must generate machine language from a high level language. Like earlier we see example that C code was using the compiler, it was converted to the assembly language. So basically, these are the people who write the compiler, so they must be familiar with the assembly language. The next is the writer of the time or space critical code. Basically, when performance goals are extremely demanding, so programmers may need to write specific sections directly in assembly language to achieve the required speed or the memory usage. So the fourth is the special purpose or embedded processor program in system with unique functions and heavy dependencies on the iOS devices. High level languages may be inadequate or useless. So assembly language provides direct control over the hardware. Okay, so these are the people which different group of the people who use the assembly language. So are there others? Yes, there are the many others, like the reverse engineers, security researchers, and operating system developers also work with assembly language when analyzing the malware, understanding system vulnerabilities, or the writing low-level system code. And of course, not the least, the students, you guys who will be learning the assembly language to understand all this and in future to develop the more efficient and well optimized system. So that's it for this part of the lecture. Thank you so much. Assalamu alaikum wa rahmatullahi wa barakatuh.